Okay, so we are studying a system of linear equations. That's just two or more lines on the same graphing grid. Mason, I need to go up here.
What? Oh, okay. Well, I was actually just trying to get my time off, so I was going to be done.
Well, you got to ask me about that first. Just go ahead and put it in there. Finish up and then put it in there. Okay, a solution of a system is any ordered pair point that makes all the equations true. So any ordered pair that makes all the equations true. So in this case right here, the solution to the system would be 3, 2, because 3, 2 is the point of intersection, and it's the coordinate that would make both of those equations true. So solution of a system is any ordered pair that makes all of the equations true. Here's another way to think about it. If I were to plug in 2 for y here, and 1/3 of 3 plus 1 on the other side, is this equation true with this solution put in for x and y? 1/3 of 3 is 1, right? 1 plus 1 is 2, so 2 equals 2, it checks out. Or right here, 2 equals -3 plus 5, does that check out? Yeah. So that's what we mean by a solution, is if you plug this coordinate in for x and y in both equations, it will make both of them true. Or, visually, it's the point of intersection. So it has a nice visual component to it. What about these? If they never intersect, we call that parallel lines or no solution. There are actually 3 things that can happen. You can have one solution, no solution, or this third case here, where do they cross? They cross everywhere. The little green line is just kind of poking out here to show you that he's there. But it's like having 2 lines that are the same. And so, infinitely many solutions. Here's what we mean by that. We could use the symbol. You won't have very many of these, but the symbol for infinity, you could use that, and I would know what you mean. IMS. I suppose. For me, that would work. You know, in general, you may not know what you're talking about, but. So, guys. What this means is that if for any x you pick, you could pick an x, there's a y that goes with it, because the y is dependent on x. I'm going to do that 40 times. So pick an x, the y is dependent on x, and it will work. If you pick a different x, there will be another y that will be on the line. So you pick any x you want, there will be a y that will go with it that will work in both equations. All right. So we're going to use our quick graphing method here. The y-intercept for this first equation right here is 2. So we place a dot at 2. So please do that. Okay, we've got a y-intercept of 2. So we're going to place a dot at 2 on the y-axis. What's the slope for this guy? 1/1. So from that dot, I'm going to go up 1, right 1, up 1, right 1, up 1, right 1. Or I could go down 1, left 1. There's a reason why I'm doing so many points. I don't know where the 2 will cross. Okay. I'm just going from this point at 2. I'm going up 1, right 1, up 1, right 1, or down 1, left 1. Okay. But from this point at 2, I'm just doing a slope of 1. I'm doing so many points because I don't know where the 2 lines will cross, and I want my line to be as accurate as possible. So typically what I suggest is just go ahead and go through the whole area of the graphing grid I give you. I usually give you a graphing grid that maybe goes 6 or 8 each direction. So if you just keep doing the dots there, at least for the first line that you graph, and then the other one is going to start where on the y? -2. and then it has a slope of 3 over 1. So from here I'm going to go up 1, 2, 3 and right 1, and then up 1, 2, 3 and right 1. And I usually just stop once they cross. You getting this, B?
Yeah.
So once they cross, I just go ahead and stop and then label the point on my graph 2, 4. So my solution is 2, 4. And here's how you check it. If I plug in 4 for y and 2 for x, does the left side equal the right side? That's the check. You just plug it in. Now, it can't just work for one. It has to work for both. If I plug in 4 for y here and 2 for x here, let's see, 4 equals 6 minus 2, so 4 equals 4. So in both cases, it works. So I know that I've done it correctly. Why don't you take just a moment to see if you can find where these two cross. If you need any help, just raise your hand and we can help you out. Try that one on your own. You can graph each line. Right here, you gotta graph that. You're good. Label where it cross. Put a dot at 4, y-axis. So 2, 4. Should be a dot right here at 4. That's the slope. At 4. So the slope says go up 2 right. So from there you go up 2 the right one. Or you could from there go down 2, left one. Go down 2 left. It's got to be in line to another dot base. From there you go down 2 more. And then draw your line. This one's interesting because if I go up to right 1, okay, if I keep going up to right 1, I'm quickly off the graph, but the intersection point is actually in the other direction here. So you want to go down to left 1. And this one, we've got it dot at 2. Okay, so this one we have a dot at 2, and then we're going to go up 1, right 1. What do you notice if I keep going up 1, right 1 here? What's the problem? It goes away. So I need to go left 1, down 1, left 1, down 1. Oh, there they go. So you may need to adjust on the fly. So negative 2, 0 is the solution. Negative 2, 0. And if you check it, it will work. So any questions on that? Make sure, if you're going up 1, over 1, and they're getting away from each other, going off the graph, just go the other direction. Stay in the same line. All right. This one says, wait here. I think you got it. It's your alligator. All right.
I don't get why you don't understand like this.
Right?
Okay. So this one says alligator 1 has an initial weight of 4 pounds. So we're going to put a dot right at the 4 on the y-axis. That's his initial weight. his rate of growth is a fractional rate of growth, right? It's 1.5 pounds per month. So what I would do is maybe go by 2-month increments. So 2 months, he would grow 3 pounds up to 7. You with me? So 1.5 pounds per month. In 2 months, go up to 7. And then 2 more months later, he would be up to 10. And then we'll draw a line through those 3 points. Alligator 2, his initial weight is 6 pounds, so he's a little bit heavier, but he's growing at a slower rate. He's growing at 1 pound per month, so that's a slope of 1 up, 1 over. It almost looks like they touch here. They actually don't quite touch here, not until here when they hit 4 months. This kind of shows us that there might be a better way of doing this, a more accurate way, because this graph, it's a little hard to tell where they finally end up crossing, but they cross right here at 4:10. So it says, after how many months did the alligators weigh the same amount? It would be 4 months. 4 months. And you could probably do that just by adding and thinking about it, okay, without the graph. But that's the idea. You can kind of see this guy, or this one right here, catching up to that one because his growth rate is faster. So that's a real-life sort of example of where we'd use a system of linear equations. In the business world, they could actually be quite a bit more complex. There could be lots of different lines. You're trying to find, where they cross. That's a pretty simple applied example. We're going to skip this one. Some of you who are working ahead may have found this one. It's kind of hard to tell when they finally cross. I believe it's off the graph. So we're going to skip that one. And I'm going to look at the case where there's no solution versus infinitely many. So one of these graphs will be a no solution one, and one is infinitely many. And it's, you gotta pick that out.
Ew! That's not
All right. Yes. If they have the same slope, and yes, okay, guys. If they have the same slope, no, wait, that's fine. If they have the same slope, it's true they'll never cross or they're the same line. To never cross, they would have to have different y-intercepts. So right on this one, we end up with 1/2 x plus 1. These two, I mean, if you compare them, they're exactly the same line. They'd have a dot at 1, go up 1 over 2. They are the same line. If I were to, you can see that they're the same line when you do the algebra. So this one is the infinitely many solutions. And this one up here is already in slope-intercept form. They do have different y-intercepts. 1 at 1, then you go up 2 over 1, up 2 over 1. Unfortunately, they're really close together, but they do not cross. The other one is up at 2, and then up 2 over 1. Very close together, but they are parallel. So this is the no solution case. So you can visually, and that's what this question is down here, you can visually tell, just looking at it, that there will be no solution here. How can you visually tell there's no solution in part B? Yeah, they're parallel. Well, when you graph it, but how can you tell without even graphing them? Same slope, different y-intercept. And then here, if they're the same equation, then it's infinitely many. So you might be able to apply that concept down here. Maybe you can get away with not even graphing these to tell which one is which. Yeah. So looking at the first one, will that be the no solution case or the infinitely many? Same slope. different y-intercept, no solution for the first one. This one you've got to solve it first. So I would write something in your summary about the 3 different cases. Maybe draw a picture of parallel lines, no solution. One single line, if they're both the same line, it's infinitely many. And then 2 crisscrossing lines makes a single solution. So go ahead and write up your summary now.